So right now, the absolute smartest AI in the world has, well, it basically has the exact same flaw as a goldfish.
Yeah, that's a pretty accurate way to put it.
Right. Like you can feed it this massive, incredibly dense textbook in just seconds, and it will completely ace a test on that material immediately.
Oh, absolutely. Perfect recall in the moment.
But then, the second you close that chat window, its actual quote-unquote brain hasn't changed by a single synapse. Like nothing's stuck.
Right, it's gone.
So the next day, if you want to pick up and work on that exact same project, you literally have to hand it that exact same stack of notes all over again. It processes everything, but it internalizes, absolutely nothing.
I mean, it is basically the defining limitation of modern generative AI right now.
Yeah.
We have engineered these systems that are capable of processing just staggering amounts of information in the moment, but their core intelligence, the underlying neural network itself, remains completely static. It's just a localized, temporary illusion of learning.
A temporary illusion. That's exactly it. And today we are bringing you on a deep dive into a state-of-the-art paper that essentially, well, it cures this amnesia.
It really does. It's a huge step forward.
We are looking at this fascinating framework called TM. The paper is titled Scaling Self-Evolving Agents via Parametric Memory. And this comes from the Character team at Alibaba Group and Peking University.
Highly respected teams in the space, yeah.
Definitely. And the mission of this deep dive today is to show you how AI is finally moving from just reading a prompt to, like, literally rewiring its own neural pathways on the fly. Okay, let's unpack this.
To really appreciate the leap that TM makes, I think we first need to clearly define the baseline we're leaping from.
Right, the status quo.
Exactly. Currently, memory-augmented AI agents operate almost exclusively in what we call prompt space memory.
Prompt space memory.
Yeah, so whenever you're interacting with a model, the actual parameters, the billions of mathematical weights that dictate how the AI actually thinks, those are totally frozen.
See, I always picture it like a printed encyclopedia.
Oh, I like that analogy.
Right, like you can write all sorts of notes in the margins with a pencil. You can shove sticky notes between the pages while you're working.
Yeah, exactly.
That's your prompt space memory, your working context. But the printed text on the physical page, the core foundation of the book itself, that never actually changes.
That is a highly accurate way to visualize it. And, the researchers highlight this fundamental disconnect by opening their paper with a really great quote from the Nobel laureate Eric Kandel.
Oh, right, the memory researcher.
Yes, and he said, we are who we are because of what we learn and what we remember.
That's profound.
It is.
Yeah.
Because in biological brains, experiencing the world physically alters the actual substrate doing the computation. Your neurons physically form new connections.
Right, thought word changes.
Exactly. But current AI just breaks that biological coupling entirely. The learning and the memory are totally separated.
But people often counter that, right? They point to systems like Aragari retrieval augmented generation.
Sure, yeah, people bring that up a lot.
They say, well, if the AI can just search a vector database and pull up a fact I told it an hour ago, isn't that a form of memory?
I mean, it functions as a lookup table. It's not true learning. The AI hasn't shifted its actual behavioral instinct at all.
It's just fetching documents.
Exactly. And the fatal flaw of prompt space memory, whether you're, squishing history into a textual summary or fetching passages from our ARG database, is the context bottleneck.
The bottleneck, right.
If a subtle, tiny detail gets dropped from a summary just to save space, or if your retrieval query is just slightly off and misses the relevant paragraph,
the AI is just blind to it.
it ceases to exist for the AI. It literally cannot reason about that fact anymore because the evidence is absent from its working context.
Because it falls out of the context window, so it falls out of reality. It's just gone.
Exactly.
So, okay, the obvious answer seems to be, well, just thaw the parameters. Let the AI update its printed text while it talks to you.
Simple in theory, right?
Right. But I mean, any developer listening to this is probably thinking that updating a massive multi-billion parameter neural network live in production sounds like a complete recipe for a catastrophic system crash.
Oh, it usually is. It's incredibly unstable.
So how does the TMM framework actually pull this off without just totally breaking the model?
Well, this brings us to the actual architecture of self-evolving parametric memory. The system doesn't try to rewrite the massive core brain of the model all at once.
Okay.
Instead, it introduces this agile, dynamic layer of what we call fast weights, right alongside the frozen base model.
Fast weights, like they utilize LoRA, right, low rank adaptation.
Precisely. They use LoRA.
Okay, so let me get this straight. During a really long session, say I'm doing a massive ongoing coding project with the AI, it is building up a working context.
Yes.
But instead of just letting that context grow infinitely until the memory buffer just explodes, TM institutes a very strict context budget.
Exactly right. They set a trigger threshold, which is usually around 4096 tokens.
Oh, you can't 4096.
Yeah, so when the ongoing conversation hits that exact limit, the agent automatically pauses its normal operation. It shifts into a dedicated memory writing mode.
So it actually stops to think about what just happened.
It does. It reviews the recent history, it distills the key insights into highly structured supervised data, and then it executes a lightweight online training update strictly on those fast LoRa weights.
Wow.
What's fascinating here is...
Wait, so it's...
Go ahead.
No, I was just going to say, so it's updating those LoRa weights while the base model is perfectly safe.
Exactly. What's fascinating here is that the massive foundational parameters remain completely untouched. That ensures total stability.
Right.
But this newly updated LoRa layer, it acts as a personalized, fast-track memory system layered directly on top.
That is so clever.
And once that microscopic training run finishes, the AI actually wipes its working context completely clean.
Wait, really? It just deletes the whole context?
It does. The sticky notes are thrown away. But the knowledge isn't gone, because when the AI generates its very next word, it is sampling from a newly adapted policy. It has fundamentally altered its own future behavior.
It's basically performing real-time brain surgery on itself while holding a conversation with you.
That's a great way to put it.
But the mechanics of this still sound highly precarious to me. Like, if I only give the model a handful of gradient steps to update those fast weights, how does it avoid just spiraling into chaotic noise?
That's the big risk.
Right, because usually if you train a model for just a few steps on a tiny bit of data, it either learns absolutely nothing or it completely overrides its own logic and goes crazy.
That is the central technical hurdle of online learning, hands down. And they solve it with their specific initialization strategy, utilizing SVD.
SVD, singular value decomposition.
Yes.
I am definitely going to need an analogy here, but let me try to frame my understanding first.
Sure, go for it.
Standard LoRA usually starts with its matrices randomized or just zeroed out.
Right.
So the initial training steps are just the AI kind of stumbling around in the dark, trying to find a mathematical direction that makes any sense. It's like dropping a car into a dense random forest and telling it to find a city.
That is precisely why standard random initialization fails in these real-time scenarios.
Because it just crashes into trees.
Exactly. Those first few vital, limited updates are totally wasted just trying to locate a meaningful subspace to learn within.
So how does SVD fix that?
Well, SVD completely eliminates that stumbling phase. SVD is a matrix factorization technique. What TMM does is take the pre-trained weights of the massive base model and perform singular value decomposition to identify the high energy directions.
High energy directions, meaning the pathways that already carry the most variance in information.
Yes, exactly. It isolates the most critical mathematical pathways the model already uses to process major concepts. Oh, wow. So instead of dropping the car in a random forest, SVD analyzes the map and instantly paves a custom-built highway pointing directly to where the most important concepts already live in the AI's existing brain.
That captures the mechanics beautifully. They anchor the online updates directly to those pre-existing major highways.
That makes so much sense.
Mathematically, they freeze the projection matrix, which is the direction of your highway, and they only allow the online training to update the coefficient matrix.
Which is like how much traffic is allowed to flow down that specific path.
Yes. And the authors actually include a formal mathematical proof in the paper showing that this SVD initialization achieves significantly smaller approximation errors than random initialization.
So it's mathematically guaranteed to learn faster.
It guarantees rapid, highly effective learning in just a few steps.
Okay, here's where it gets really interesting. Because having a perfectly paved highway is an incredible engineering feat, obviously. But it ultimately matters what kind of cargo you are sending down that highway.
Right, the actual data. Yeah. You mentioned earlier that the AI distills the session into supervised data. What exactly is it writing into its own memory?
The format of that memory data actually turned out to be the most critical variable in the entire framework.
Really? More than the SVD.
In terms of actual performance, yes. The researchers ran extensive ablation studies to see what happens when the AI tries to memorize different formats.
Okay.
First, they tried raw next token prediction.
Wait, meaning they basically fed the raw, unedited transcript of the conversation just right back into the model and told it to memorize the exact text.
Exactly that.
Let me guess, it just learned to mimic the formatting and completely lost the actual meaning.
It was a spectacular failure.
I knew it.
On a comprehensive long memory benchmark, that raw text method achieved an F1 score of just 10.37 out of 100.
Oh, wow. 10.37.
Yeah. For context, an F1 score that low means the model is essentially just guessing blindly. It trained the AI to act like a parrot, regurgitating dialogue structure rather than internalizing any actual knowledge.
Okay, so raw text is out. What else did they try?
They also tested having the AI generate free-form paragraph summaries to use as training data, but the results there were only mediocre. It didn't really stick.
So what was the winning formula?
Structuring the memory as precise QA pairs, question and answer.
Oh, interesting.
Yeah, the memory writing prompt specifically instructs the AI to generate grounded, supervised, fine-tuning QA pairs based on the context.
It's writing itself flashcards.
Functionally, yes, that's exactly what it's doing.
That's amazing.
If a user spends an hour talking about their personal life, the AI doesn't save a messy paragraph. It explicitly constructs a pair. Like, why does Melanie go for long runs, and maps it to the output to de-stress and clear her mind.
Wow. And structuring the data this way, I imagine that aligns perfectly with how the neural network will actually need to recall and deploy those facts in future conversations.
It forces the model to learn the specific activation pathways for answering questions, which is how we interact with LLMs anyway.
That is brilliant because it forces the AI to encode the actual relationship between concepts rather than just the text itself.
Exactly.
But okay, this immediately introduces a massive filter problem.
How so?
Well, if I talk to an AI for 3 hours, like 90% of that is filler, pleasantries, or just dead-end tangents.
Sure.
How does the model know that Melanie's running habit is the crucial detail it needs to burn into its parameters, rather than a random tangent about the weather being cloudy that day?
If we connect this to the bigger picture, this specific challenge is where the paper really elevates from just clever engineering to genuine artificial intelligence.
Oh, I'm listening.
To solve that filtering problem, the researchers introduced a reinforcement learning phase, or RL. The base model undergoes training using a stop gradient policy optimization objective.
Whoa, okay, stop gradient policy optimization. That sounds incredibly heavy. Is it updating the whole model's conversational logic during this phase?
No, and that is where the stop gradient part is crucial. In this RL phase, the rollout couples two entirely different kinds of actions.
Two actions.
You have ordinary actions, which is just the AI chatting with you normally. And you have extraction actions, where the AI stops to write those QA flashcards.
Right.
The stop gradient acts as a literal mathematical firewall. It prevents the model from accidentally destroying its ability to hold a normal conversation while it's trying to optimize its flashcard writing skills.
So it totally isolates the learning. But how does the policy optimization actually teach it what a good flashcard even looks like?
Normally, reinforcement learning rewards a model purely for getting the final task right at the very end. But TMEM's brilliance is that it rewards the AI for producing high-quality supervision data for its future self.
For its future self.
Yes.
Right.
It evaluates whether the QA pairs generated at step A actually improve the model's performance on a complex task later at step B.
It's literally playing 4D chess.
It really is.
It gets rewarded today for writing optimal study notes that will guarantee a better performance from the version of itself that will exist 10 minutes from now. That is wild.
Exactly the right framing. The base parameters are optimized to just ignore the small talk, identify the critical variables, and output the precise QA format that makes the subsequent SVD highway adaptation successful.
And getting that timing right has to be a pretty delicate balance, right? I actually found the section on context budgets fascinating because they discovered that the optimal trigger for writing these memories isn't just as often as possible.
Right, it's not just spamming updates.
It follows a strict bell curve, like a Goldilocks zone.
It does. If you set the trigger too early, say, forcing it to write a memory update every 1024 tokens, the system overcompresses fine details.
Because it hasn't heard enough yet.
Exactly. The AI is constantly trying to summarize before a complete thought has even fully formed in the dialogue.
It's like trying to write a comprehensive book report when you pause to summarize every single page. You just completely lose the overarching plot.
That's a perfect analogy. Conversely, if you wait too long, say 12,288 tokens, the working context becomes deeply polluted.
Right, too much noise.
The attention mechanism of the model gets diluted by thousands of words of filler, ahs, and random
You
tangents.
can't see the forest for the trees.
Exactly. It becomes incredibly difficult for the extraction prompt to ground itself and pull out clean, accurate QA pairs. You have to locate the peak of that bell curve, which usually hovers around 4,000 tokens for most tasks, to achieve the highest quality self-evolution.
The theory is just undeniably elegant. I mean, we have an AI that intuitively senses when its context buffer is full, pauses, generates high-quality flashcards of the most salient data, and then physically alters its own neural network using a highly efficient SVD highway.
It's a beautiful system.
It is. But as a skeptic, I always want the receipts.
Naturally.
How does a self-evolving AI actually perform when tested head-to-head against the old frozen models we use today?
Well, the empirical results are very robust. They tested TMEM using the Qwen34B and Qwen38B architectures.
Solid model.
Very solid. And they benchmarked it against standard models with zero memory. Models that rely on constantly rewriting text summaries, such as MemAgent, and models that rely on external vector databases for retrieval like AMEM.
And how did it do?
Across the board, TM consistently dominated both the summary and retrieval baselines on complex, long-context conversational benchmarks and multi-objective search tasks.
Yeah, the paper had some incredible specific examples that really crystallized the advantage for me. There's this one test from the Long-Neville benchmark where the AI had to track a user's market earnings over a massive sprawling dialogue.
Oh, the market earnings scenario. That perfectly illustrates the failure points of current systems.
Right, because it's so messy.
Exactly. The user in the prompt discusses selling various items across different days at different markets, and it's all buried in casual chat. They mentioned selling homemade jam at the handmade market for $225.
Okay, 225.
Then much later in the transcript, they mentioned selling potted herbs at the summer solstice market for $150.
Ooh, 50. Got it.
Then, even later, fresh herbs for $120.
And a standard summary-based AI just totally loses the thread there. It summarizes the jam away to save space, or a retrieval model fails to fetch the potted herbs because the final query asking for total earnings wasn't specific enough to trigger the right keyword search.
Both of those failures happen constantly in standard models, but TMEM succeeded because at every context boundary, it converted that chaotic, sprawling history into clean, distinct facts.
The flashcards.
Yes, it literally baked into its parameters. How much did I earn from homemade jam? $225.
Wow.
So at the very end of the massive chat, when asked for the total, the model's internal policy inherently knew all three discrete values. It effortlessly calculated 225 plus 150 plus 120 equals $495.
That is wild. It didn't need to scour a massive transcript or query a database at all.
Not at all. The knowledge was natively embedded in its adapted weights.
It is the profound difference between knowing a fact and just knowing which book to look it up in. The AI actually possessed the knowledge.
Yeah.
And TM also showed a massive advantage in tracking nuanced human preferences, right? There were examples from the Locomo benchmark.
Yes, Locomo explicitly tests long-term persona and preference tracking. TM seamlessly internalized highly specific user details.
Like what?
For instance, it remembered that a user named Caroline was actively researching adoption agencies that specifically support LGBTQ+ families.
Oh, that's incredibly specific.
Right. And it recalled that Melanie prefers national parks over theme parks because she uses running in nature as a primary stress relief mechanism.
So it connected the running to the parks.
Exactly. Because these nuanced preferences were extracted as precise flashcards and fused directly into the fast weights, the model's entire conversational persona shifted to naturally accommodate these facts in all future responses.
And it wasn't just social chat either. They tested it on rigorous analytical tasks, too.
Indeed. They evaluated it on multi-objective search tasks with complex, overlapping constraints.
Like combining different clues.
Yeah. For example, the agent was asked to identify a 1996 film loosely adapted from Shakespeare, directed by James Gunn.
That's a lot of constraints.
It is. Because TM is actively evolving and synthesizing knowledge during the search process, it successfully combined multiple constraints gathered across several different search queries to correctly identify the obscure film Romeo and Juliet.
Wow. Whereas a frozen model would just...
Frozen models typically become completely confused by the competing noise of multiple search results. They can't synthesize it.
Okay, so the performance is just undeniable. But I mean, saving the AI's memory is great until it grinds the system to an absolute halt.
Ah, the efficiency question.
Right. Maintaining an external vector database for retrieval usually creates massive latency. And running gradient descent in the middle of a chat session sounds like it would slow the response time to an absolute crawl. Does this real-time adaptation demand massive computational power?
This is perhaps the most counterintuitive finding in all the receipts. TMM is actually exceptionally efficient.
Really?
Well, because the framework fundamentally relies on wiping its working context clean after every update, it consumes vastly less GPU memory than a standard model that tries to keep the entire conversation open.
Oh, because it's not holding a massive transcript in its active memory.
Exactly. On the long memevil as benchmark, the baseline model that simply let the context grow used 78.5 gigabytes of peak GPU memory.
78.5.
Okay. TMM used only 22.9 gigabytes.
Are you kidding? That is a staggering reduction. It operates on less than a third of the memory footprint.
It's remarkably lightweight.
But what about the speed of generating a response? Does it lag while it's training?
It actually profoundly outpaces retrieval methods. Embedding search queries, maintaining an external vector database, and fetching documents introduces significant latency.
Right, all that fetching takes time.
On that same benchmark, the retrieval-based method required 15.33 seconds per episode.
Okay.
TMM required only 6.55 seconds.
That's less than half the time.
It is marginally slower than a pure text summarization method, but you are trading a fraction of a second in online training overhead for a monumental leap in reasoning accuracy and true knowledge retention.
So what does this all mean? We have covered a massive amount of ground today. We started by examining the goldfish memory of current AI, systems that rely entirely on fragile text lookups, while their actual neural architecture remains just frozen in time.
Right.
And we explored how TMEM just completely shatters that paradigm, proving that an AI can internalize its experiences in real time. It intelligently distills sprawling conversations into precise QA flashcards and utilizes a mathematically optimized SVD highway to physically wire that knowledge right into an agile layer of fast LoRA weights.
It is the critical transition from an AI that merely reads its context to an AI that fundamentally internalizes it.
Building on that, why should you, listening to this deep dive, really care about this architectural shift?
It's a good question.
Because it completely redefines the trajectory of the AI tools you will be relying on in the very near future. Soon, your AI will not just regurgitate the PDFs you upload or summarize the text you paste into the window. During a single extended session, whether you are architecting a complex software platform, plotting a novel, or running intricate financial models, the AI will structurally evolve.
Yes, it will change with you.
It'll become fundamentally smarter and uniquely attuned to the specific nuances of your project the longer you work together.
The system essentially ceases to be a static utility and transforms into a dynamic collaborator.
Which brings us to a final, slightly provocative thought to leave you with today. If an AI can continuously update its own neural pathways, if it can physically internalize your preferences, the quirks of your projects, and your specific way of solving problems during a single extended session, at what point does a simple chat interface stop being a software tool and become a distinct, continuously evolving digital persona that has been uniquely shaped by your mind? Just like tutoring that forgetful student, once they finally start internalizing your lessons, they aren't the same student anymore. They have grown into something entirely new.
It represents a fascinating and deeply personal paradigm shift in how we will interact with machines going forward.
It really does. Thank you so much for joining us on this deep dive. Keep asking the big questions, and we'll see you next time.